Fine. So SN1 and SN2 and SNI. The SNI is substitution nucleophilic intermolecular. Then the points to be discussed under SN1 and SN2, the definition with examples, mechanism, and kinetics related to SN1 and SN2, then stereochemistry of SN1 and SN2, then factors influencing the reaction rate. So what are all the factors like nature of the substrates, then nature of solvent, then the nature of nucleophile. So all these things you need to discuss under the factors influencing the reaction rate. So let's start with the SN2, that is bimolecular nucleophilic substitution. So substitution, nucleophilic, bimolecular reaction. The example for this SN2, let us start with the substrate of methyl bromide, and the nucleophile is OH minus. So in this case, this is, we can call it as a RX, and R is methyl, and X stands for the Br system, and this is actually Nu minus. So this will nucleophile, and this will be the substrate. During a reaction between the nucleophile and the substrate of RX, that is methyl bromide, will lead to the formation of.
Sir, sorry to interrupt, but one guy is waiting in the what do you call that? Waiting room, sir. Can you please add him?
Waiting room? I have not seen anyone in the waiting room.
He just messaged in the group saying he has not been added.
Okay, so that okay. Now we just appear.
Okay, sir. Yeah, sorry for the interruption.
It's okay, no problem. So you suppose in such kind of, if any technical related issues there, just interrupt. Don't mind. So you can interrupt me at any time. Okay. So in case of bimolecular nucleophilic substitution reaction, the nucleophile is OH minus, and the substrate is CH3Br. So RX is the general form, and the nucleophile Nu minus stands for the nucleophile, and OH minus nucleophile in this example, and the substrate is methyl bromide. The nucleophile prefers to attack over the carbon, as this substrate has only one carbon and the leaving group present on the same carbon. So in this case, not necessary to worry about the rest of the carbon, the substrates which is having 2 or more carbon. Then only in such cases you need to give the preference the carbon which is having the leaving group. But in this case, as it is a methyl bromide, the carbon and the rest of the thing is 3 hydrogen present over the carbon, and along with that a new one type of C and Br bond exists between the carbon and the Br. So during this, nucleophile prefers to attack over the carbon and the CBr bond cleavage heterolytically, and Br will lease out as a Br minus. So this will be the leaving group, and this is your product. Fine. This reaction generally prefers to follow via SN2 fashion, bimolecular nucleophilic substitution. Examples for various transformation you can perform if you have a substrate of simple, that is methyl bromide as a substrate, and the nucleophile, suppose if you are using the OH minus as a nucleophile, then the reaction between the substrate and OH minus nucleophile, you can prepare the methanol. So an alcohol can be prepared. Similarly, suppose instead of using OH minus, if you're using RO minus as a nucleophile, then the RO minus prefers to attack over the carbon which is carrying the leaving group leaves out, then you will get a product. The product will be generally CH3OR. So that is an ether. Then instead of using any of these two nucleophiles, suppose if you are using HS minus as a nucleophile and prefers to attack over the same substrate of CH3Br, then you will get CH3SH, a thiol, or you can call it as a mercaptane. Instead of using HS minus as a nucleophile, suppose if you are using RS minus as a nucleophile, then the same substrate prefers to attack over the carbon which is carrying the leaving group, and the product formed will be CH3SR, a sulfide or thioether. And instead of using any of these nucleophiles, if you're using an I minus, so I minus can also be used over here as a nucleophile, and I minus prefers to attack over the carbon and leaves out this Br minus. The product will be CH3I, an alkyl iodide. An alkyl iodide. Suppose this is iodide exchange reaction or halide exchange reaction. So in this case, you are replacing by the I minus. Then if you have an CH3Br in the starting material, if you want to convert the CH3Br into CH3I, then you need to use the I minus as a nucleophile. Then CH3I will be the end product, that is an alkyl iodide. Instead of in all these nucleophiles, if you are seeing carefully, this species carries a negative charge, right? O minus, RO minus, then HS minus, RS minus, then I minus. So this is all negatively charged nucleophiles. But if you are looking to the next nucleophile, that is NH3, the NH3 does not carry any negative or positive sign. So this is actually neutral nucleophile, right? So the nucleophile NH3 prefers to attack over the CH3, which carries in a leaving group. During the reaction, the NH3 prefers to attack the carbon, which is carrying the leaving group. Then after the reaction, you will get CH3, NH3 plus an alkyl ammonium ion is the end product. Similarly, in the one more nucleophile, the OH2 or H2O. So H2O will also act as a nucleophile. Then this will also prefers to attack over the carbon, which is carrying the leaving group. Then you will get CH3OHH plus, because it has given one of its lone pair for the bond formation between the carbon and the oxygen. That's why oxygen prefers to carry a positive charge. And in this case too, then nitrogen has one lone pair, and lone pair has been involved in the bond formation between the carbon and the nitrogen. That's why in this product as well, the NH3 plus, the lone pair is involved in the bond formation between the carbon and the nitrogen. And if suppose if you are using this nucleophile of H2O, and you will get the CH3OH2 plus and alcohol generally after the proton transfer. So proton transfer means the H will leave out as a H plus, and you will regain it's the lone pair. In such cases, the product will be an alcohol. So from this, you can visualize that if you have a nucleophile, various types of nucleophile, the various type of products can be prepared with the help of substrate like RX, and all generally is in primary halides. So various reactions one can perform just by replacing the nucleophile and keeping the same substrate. You can synthesize various products. Is it clear? Any doubts with respect to this example? Okay. So now let's move on to the mechanistic part involved during this SN2 mechanism. The nucleophile and the alkyl halide combines to form a pentacoordinate transition state. So as one of you said that the SN2 needs to follow via transition state formation before moving to the product formation stage. The nucleophile and the alkyl halide, the nucleophile is this one, and alkyl halide combines to form a pentacoordinate transition state. So this is actually a transition state. In the transition state, it is a pentacoordinated form. Pentacoordinated means the carbon has a how many bonds?
5.
5. Penta coordination. So carbon, if you look into this carbon has a carbon, hydrogen, then carbon, hydroxyl, carbon, Br, then carbon, hydrogen, carbon, hydrogen. So the covalency of this carbon, particularly in the transition state, it has a 5 carbon. So covalency of 5. The transition state with simultaneous bond breaking and bond forming taken place in the transition state. So if you are looking into this transition state, there is a new bond formation happening between the carbon and the oxygen of hydroxyl. And on the other hand, the carbon and Br, a new bond the bond breakage is taking place between the carbon and the Br. So the bond breakage and new bond formation occurring between the carbon and the oxygen in the transition state. Once this process is over, then only the reaction proceeds to the forward direction, and you will get the alcohol and the leaving group of Br minus. This is the rate determining step. So rate determining step in this case is during the reaction of a nucleophile and the methyl bromide, you will have a transition state, and the formation of transition state is the rate determining step, and that is the slow step. It entitles two species, that is Rx and Nu minus. If you see the transition state, it has both the species like Rx as well as nucleophile. The dotted lines indicate a partially formed or partially broken covalent bond. But I think you cannot find out the dash line. This actually corresponds to the dotted line. Indicates partially a bond formation and bond breakage taken place. Bond formation between the carbon and the oxygen, and the bond breakage between the carbon and the Br. So, and these bonds are covalent bonds. CBr bond and CO bond are a covalent bond. But only thing you need to remember that in the transition state, the CBr bond breakage and CO bond formation. Then only you will get the product. So from this, it is a single step reaction, and transition state is the intermediate, reaction intermediate. And it's the transition state, the carbon has a penta-coordinated, and the bond breakage between the CBr, that is, or the C and the leaving group, and carbon and the nucleophile, there is a new bond formation. And if you see the if it is an substrate is optically active, then generally you can prefer the inversion center, the carbon, which is in the, suppose if it is in the optically active substrate, if you are taking, then if it is in R configuration, optically active form, then after the reaction you will be having an S. Suppose if you start with the S, then you will be having an R. Inversion center take place during the reaction between the nucleophile and the optically active substrate.